Alright, we're going to start formalizing the definition of a limit. And we're going to start that by actually doing it what I consider to be one of the most difficult and time-consuming ways possible. However, this is very important for you to get an understanding of what's happening, so I want you to actually try this yourself. I don't want you to just watch this video and let me do it all for you. I'm going to tell you when to pause, and I want you to try to work. So, introduction to limits of a function. In order to better understand functions, we often want to know the behavior of the function near a particular point. We'll call it C. But maybe not at that point C itself. You want to know what's happening around that point. For example, when you approach C, and maybe that point C is undefined, what does the curve do? Does the curve go towards C and then just have a hole, like an open circle? Or does that function approach that C value and shoot to infinity? Or maybe the function goes to negative infinity? What does the function do as it gets closer to that one point where maybe the function's undefined? So here we have an example. How does the function f of x behave near x equals 2? So I want you to think of this as being the C value. We want to know what's happening as our x's approach C. Does our function approach a particular number, or does our function blow up to infinity or negative infinity? How do we figure this out if we don't have a picture? Well, this is a numerical method for finding a limit. What I want you to do is I want you to build a table like you see here. So you see I've listed some x values, and I want you to notice where C is. C is in the middle of my x values. But look at what x values I've chosen. On the left side of our table, we have 1, which comes right before 2, right? But I can get closer to 2. So what I did was I made my x's go closer and closer to 2. My x's are approaching 2 as we move. So my x's are approaching 2 as we move from the left to the right along our table. And then we get to 2. On the other side of 2, I want you to look at what's happening over there. I have 3. 3 is the number that comes right before 2, or right after 2. But there's some numbers that are actually closer to 2. So notice, if I go from the right side of my table towards 2, my numbers are getting closer and closer to 2. How close can we get to 2? Well, that's up to you and how many values you want to type into your calculator. But as we approach 2 from the left-hand side and from the right-hand side, you're going to get that a lot. Notice that my x's are getting closer and closer to 2 as we go. If you want to get closer, you can. I just did a small table to help illustrate what's happening here. Alright, so what I want you to do is I want you to take these numbers, these x values, and I want you to plug them into our function, right here. Okay? So take 1, plug 1 in for the x, so 1 squared minus 4 over 1 minus 2. Punch that in your calculator, see what answer you get. And then I want you to do it for the rest of the numbers. Even 2. What happens when you plug in 2? Then I want you to pause, I want you to work those out, and I want you to write down what values you get. Then I want you to look at your values. What happens as you go from the left side and the right side towards the middle of your table? What are those answers, those function values approaching? So pause the video and come back when you've got those function values worked out. Alright, so I hope you did it. I did it too. And what I want to do is I want to show you my answers. So let's just look at one side at a time. So over here, we have our answer. Whoa, what happened? Okay. Over here, we have our function values. As we follow our table from left to right, what do you notice about these values? Are they approaching a particular number? Well, they're not changing as much as they used to. As you approach 2, they change less and less. What's happening on the other side? Move my little box. So on the other side, as we follow our table from right to left towards the middle of our table where our C value of 2 is, or X value of 2, look at what's happening with these function values. We go from 5 to 4.1 to 4.001. As we move towards the x value of 2, what is our function value approaching? Or is it approaching anything? It could be blowing up to infinity. Does that look like it's getting bigger and bigger and bigger? No, the values are calming down. They're going towards a particular number. And actually, both directions are approaching the same number. What's in between 3.999 and 4.001? what do you think the limit of this function is? Just bigger than 3.999 and just smaller than 4.001 would be 4. This is what we call the limit of this function as x approaches 2. This is a huge concept. Will we always do it this manner, numerically? No. We're going to try and work on some techniques using some limit laws and some algebra tools to try and simplify this work. We might even see this problem again using an algebra technique. Alright, so what else do I need to tell you about this? This is actually a technique you can pretty much always use. Just make sure you get enough values approaching your C value so that you can see the pattern. This, however, is very time consuming. So on an exam, this is not recommended unless it's required that you use this numerical approximation approach. In general, this is not usually a good way to do it because it's time consuming. Alright, so this concept of a limit, we have a lovely notation that we're going to use here. We have the limit. I'm going to read this to you. In the green boxes, the limit as x approaches c for the function f of x is equal to L. So L is your limit. So the limit as x approaches c for your function f is equal to L. Now, our problem that we just did, we can actually write the limit notation as well. So remember, our function f of x was x squared minus 4 over x minus 2. And our c value was 2. We were approaching 2. So to write the limit notation for this, we write the limit, that's how I write limit, it's kind of squiggly, as x approaches our c, which was 2. Remember, we were letting the x's go towards 2. Then we write our function, so x squared minus 4 over x minus 2 equals our limit. We found our limit. If you don't know your limit, you can write L, but if you do know your limit, which we found it, was 4. There you go. So the limit for our function f of x as x approaches 2 equals 4. Note that when we actually found our limit, we did not actually plug in the c value. The c value is only a directional to give you guidance of what x is approaching. We never actually need to plug it in to calculate a limit. A limit does not care what's happening at the particular x value you're approaching. A limit cares what's happening around it only. There are times where your function value and your limit value will be the same, but you never want to start by just plugging it in if you're doing a numerical approach because you're interested in what it's doing as it comes closer and closer and closer. Later on, we will do a method where we plug it in, and we'll talk about that. But in this concept here, we want to see what's happening as we get closer and closer and closer. So don't just go straight to your x value. Because if you plug in your x value, it's very possible that your curve has nothing to do with what's happening at your x value when it comes to approaching it. They could be two completely different topics. So, in general, when we talk about a limit, it's not actually talking about going straight to your x and plugging it in. It's talking about what's happening as you get closer and closer to that x value. Alright, so now what we want to do is we want to start building up some tools of some basic functions that can help us simplify the process of finding limits. One of the most simple functions we can talk about is the identity function. The identity function is this guy right here, f of x equals x. Meaning, if I ask you what is f of 2, the answer is 2. If I ask you what's the function value of -1, the answer is -1. The identity function is whatever you plug in is what you get out. So, what is the limit of an identity function if you're approaching a particular value c? Let's pick one. Let's actually do limit as x approaches 5 for x. So this is our function f of x right here that I've plugged in. What is the limit of this function? Well, we have a graph here on the right to help us understand what is occurring. So remember, when you're trying to let x approach a number, for example 5, so let's put 5 on the graph, let's call this 5. We follow the x values towards 5. And we want to know what the function values we're approaching. So let's just follow our graph. That's the easiest way to do this. So if I go from the left side of my x value and I follow my graph towards that x value, and do the same thing on the right. If I go on the right side of my graph and I follow the curve towards my particular x value I'm interested in, both sides of that appear to be approaching what? This one particular point. y values as well. If our x values approach 5, then our y values are going to approach this particular y value at that point that we've discovered. Guess what? This is the identity function. So if that point has an x value of 5, he also has a y value of 5, because whatever you put in is what you put out. So the limit of an identity function is whatever you're actually trying to approach. So the limit of x, our identity function, as x approaches 5 is x itself. If you wanted to build a table and actually work this out, you could. So if you did x values and then your function values, let x, let's see, it's approach 5. So if we're trying to approach 5, who comes before 5? 4. Okay, we want to get closer to 5. So who's closer to 5? How about 4.9? And then closer to 4.999. Then you can get closer if you wanted to, but this is just to illustrate what's happening. According to our function, which is just x, whatever we put in is what we get out. So the answers to these are 4, if we plug in 4. And then if we plug in 4.9, we get 4.9. And then 4.999. If we plug in 5, well, that's what we want to find out. So watch what your function values are doing. What are our function values approaching? As the x values approach the 5, the function values appear to be approaching 5 as well. So the identity function is one of the easiest ones to find. This is one of the cases where the point that you're trying to approach is actually perfectly in line with your function values, and it actually is the function value. So as your function approaches that x value, it's actually approaching the function value at that point as well. This is going to be something we discuss a lot more when it comes to continuity, which is coming up shortly. All right, let me talk about another one. So here we have what's called the constant function. So f of x equals k. K is a number. Any number is constant. Pick a number, plug it in there. So for example, if I want to do f of x equals 10. So 10 is my constant. What does this function say? It says plug in an x. No matter what x you plug in, the answer will be 10. So how does that affect a limit? Well, no matter what x you plug in, you're going to get 10. So if I were to build an x table, and let's build a limit. So let's say we want to take the limit as x approaches 2 for our function 10. What's the limit going to be? So our x's, we're going to approach 2. So what comes before 2? 1, and then 1.9, and then 1.999. That'll work. Well, according to the function, for each of these x's, no matter what x we plug in, the answer is 10. So each of these has an answer of 10. So our limit, as x's approach 2, what is the function value approaching? Well, the function value is constant, meaning that no matter how far or how close to 2 you come, no matter what, you will always be approaching the same value, 10. If I were to do it from the other side, let's see, what comes after 2? 3, and then we have 2.1, and then closer would be 2.001. So I'm approaching the x value of 2 from the right side. Well, again, the function value for each of these is just 10. So our function, as x approaches 2, our function values are just 10 all the way. So they are staying constant, because that's the constant function, and they are approaching the value of 10. So that would be our limit of this function, 10. So what does that mean? The limit of a constant function is the constant itself, 10. Okay? So those are 2 rules. Identity function. The limit of a function x is whatever you're trying to approach, the x value. The limit of a constant is the constant. So I have 2 examples. I want you to stop, I want you to pause, I want you to try these. You're asked the limit of 2 different functions, and you're given an x value of approaching -1. What is the answer to these limits? So pause the video, come back when you're done, and check out the answers. Alright, hopefully you pause the video and you try these. Very important that you practice these concepts. This is not something that you can simply learn by me teaching you. You must actually try them. So find the limits below. The limit as x approaches -1 for the function 3. Remember, this is 3, meaning the function is always 3. This is the constant function. So, if your function is always 3, what's the limit? It's going to be the constant, the 3. Who cares what x is doing? The function is always 3. It doesn't doesn't change. Therefore, no matter where your x is approaching, the limit will be the constant value 3. Number 2 here, the limit as x approaches -1. Now in this case, our function is x. This is the identity function. So if x is approaching 1, the question is, what is this x approaching? Well, if this x is approaching -1, then our x for our function has to be approaching -1. If x is approaching -1, then x has to approach the same thing. I know, it sounds funny, but that's the way the identity function works. It tells you what x is doing, and then the answer just happens to be the same thing as the input. Whatever you put in is what you get out of an identity function. Alright, there are times when a limit can fail to exist. So what we're going to do, we're going to look at a couple cases here, and I'm going to do it visually, because visual is a huge help in talking about why things are failing to, why limits are failing to exist. So example, discuss the behavior of the following functions, explaining why they have no limit as x approaches 0. So our first case here, this is called the unit step function. So the function is 0 as long as x is less than 0. Then we have an open circle here. What does an open circle mean on the graph? It means there's no point. So at that point, if x is 0, we jump up to 1, a unit step. And then we have, for all positive x's, x is greater than or equal to 0, the answer is 1. So what is the limit for this unit function, u of x, as x approaches 0? Let's look at our graph and see what happens. As our curve approaches the x value of 0, what does this function value approach? So I'm going to get on a curve from the left of 0. Remember, this is where x is 0, right here in the middle. This is what we're trying to approach. So if we get on it from the left and we approach x is 0, what function value are we approaching? From this side, the function value we're approaching is this point right here. It's an open circle, that's okay. We're just interested in what we are approaching. And we don't actually have to get there. As we go towards that point, what is the function value at that point? Well, all of these points have the same function value. The function value is the 0. Remember, that's the y value here. Let's try and approach from the right-hand side. So if we approach from the right-hand side along our curve, we approach x equals 0. What function value are we approaching? What is the limit as x approaches 0 from the right-hand side? Well, in this case, the limit is approaching this function value at this point. Well, what's the function value there? 1. This time we have a point. We don't actually care about the point itself. What we care about is what the curve is approaching. It's approaching that point. And that point has a y value of 1. So that's the limit from the right-hand side. So this is our y value for the limit. Now, what does this mean? From the left-hand side, we get 0. From the right-hand side, we get 1. This is an example where the limit does not exist. So we write DNE, or does not exist. This is actually a very simple thing to write down if you want to show your work or explain your work. All I would expect to see is you to explain why. Visually why, we say that there is a gap at x equals 0, the value we're trying to approach. Or you could call this a jump. Different ways to describe what's happening here. If you have a gap or a jump at your x value you're trying to approach, that means your function value changes dramatically there. If your function value changes from a smaller to a bigger or bigger to smaller, either way, if your function value changes at that x value, then your limit is going to be 2 different values. You cannot provide 2 different values for a limit. A limit must be one agreed upon value from both directions. Alright, we've got 2 more here. So, in this case here, we want to again find the limit as x approaches 0 for this function. If you look at the function, it actually has a point at x equals 0. But notice our curve is not approaching that point at all. So that point will have nothing to do with our discussion of a limit, because our curve, what it approaches, is what's going to define the limit. So let's ignore that point because our curve doesn't approach it. Let's follow our curve. Our curve, if we follow it to this value where x equals 0, that would be this line here. That's what we're trying to approach, that line. Get on your curve from the left-hand side and approach that line. Where does your curve go? What is your function value approaching? Our function of value is approaching negative infinity because our function just goes down and down and down. It never gets any close, it never actually reaches a point. It just gets lower and lower and lower. That's the 1 over x type of curve. If we approach our function or approach our limit from the right side of our curve, so get on your curve from the right side and approach your limit, our curve goes up and up and up. It keeps getting closer and closer to x equals 0, but it never actually reaches it. So what does that mean it's doing? What is the function value approaching? Positive infinity. So what does that mean? This function is actually not bounded as x approaches 0. It goes up to positive infinity and it goes down to negative infinity. In order to have a limit, it must approach a number. Infinity is not a finite number. It is infinity. It just keeps getting bigger and bigger and bigger. So for now, we're going to say that this limit does not exist. Later on, we are going to define a way of describing how it does not exist, but for now, we're just going to say it does not exist because there is no limit. That's as detailed as we're going to get. Later on, we'll talk a little bit more detail on this. All right, we have one more case here. This one is really cool. This is called an oscillating function. So what we're going to do is we're going to approach our curve, letting the limit be as x goes to 0. And let's start from the left-hand side because that's the easier side. On the left-hand side, our function says if x is less than or equal to 0, then the answer is 0. So if you look at your picture, approach from the left-hand side. As you approach this line, where x equals 0, what function value are you approaching? The limit from the left-hand side, the function value that you're approaching is 0. That's fine, that's easy, we can do that, hopefully. If that does make sense, make sure you review what I've already talked about and make sure you understand what's happening before you continue on. The right-hand side is the interesting one. On the right-hand side, we have an oscillating function. What does that mean? Because it might be something that you've never heard of before. This curve, sine of 1 over x, is going up and down and up and down and up and down. As it gets closer to x equals 0, it actually goes up and down more and more frequently. The spacing between our oscillations, the up and downs, gets smaller and smaller and smaller. So they actually are not even able to draw this for you. So because they can't draw for you, it's hard to actually show you what's happening, but just imagine that this is going up and down indefinitely. It's always going to go up and down again. No matter how close to your goal, x equals 0 you can always go up and down again. Get closer to 0, go up and down again. Get closer to 0, goes up and down again. Well, if it constantly goes up and down, no matter how close you get, meaning you're taking your limit, you're getting closer and closer to your goal of 0, if it can always go up and down again, will it ever approach a finite single value for its function value? No, because if you get closer, it goes all the way up to 1 and all the way down to -1. Get closer to 0. It goes all the way up to 1, all the way down to -1. No matter how close you get, you will always range between -1 and 1. That means that you're not going to approach a particular limit because your function will never calm down from this jumping between -1 and +1. So when you see this concept of an oscillating function, as long as it's oscillating in this fashion, trig functions are totally different. They don't oscillate like this. They're periodic. That's different. But if you see an oscillating function where no matter how close you get, it goes up and down again and again and again, that is a case where you would say the limit does not exist. So the limit for this function, f of x, we say that this is oscillating between -1 and 1 this is a technical way of writing it, in every open interval containing 0. So if your goal is 0, you go just a little bit out. You oscillate in there. Function goes all the way up to 1, all the way down to -1. If you shrink that interval from 0 out just a little bit, it's still going to go all the way up and all the way down. Shrink that interval a little bit. It's saying every single one of these intervals will always go up and down, no matter how small you make it. Therefore, the limit does not exist. So D and E does not exist. So this was an introduction to limits. We have a lot more to talk about. There are a lot more tools that we're going to learn to be able to find limits more quickly than using the numerical method. And also, in these cases, we looked at pictures. We aren't always going to have a picture to help us with the graphing. So you're going to need the tools. Make sure you understand what we've talked about before you move on. Make sure you study hard, and good luck.